about some textbook level solutions like harmonic oscillator, rigid rotor, hydrogen atom, particle in a box. Actually, do you solve Schrodinger equation? Now, if you know how it is solved, then only you will understand whether you are solving Schrodinger equation or something else. Okay, that mathematical acumen is very much important. Why? The Schrodinger equation is a second order differential equation because your Hamiltonian operator contains kinetic energy that is coming with the Laplacian, so second order differential operator. That means you have to solve a differential equation. Okay. Obviously, in your textbook level solvable problems, ideal problems, there are out of infinite, almost infinite number of quantum problems. Only handful, maybe 5 or 6 problems are analytically solvable, which are there in your standard textbooks. But they will not help you in any way. Only basic understanding how to solve analytically. If you go into a simple helium atom, you won't be able to solve. You even go to the hydrogen molecule, you won't be able to solve. So what do you do in that case? Do you really solve the typical differential equation? That means you are starting with certain operator concept, differential operators, etc., etc. Do you do that? No. So we convert this to a matrix equation. Equivalently, quantum mechanics was developed by two giants, two great scientists. Schrodinger developed in terms of his own equation. That is what we call wave mechanics today. Another side, Heisenberg also developed something. That's a matrix mechanics. Actually, we are somewhere in between. We convert the differential equation to matrix equation. Then we diagonalize that matrix. Okay, so we are not actually solving Schrodinger equation per se as the differential equation. No, because differential equation, if you have say 10 electrons, like the helium atom, neon atom, you will have 30 dimensional, 30 special variable to that. So how will you do this? This journey, this transition, I will have to start from the basics. Okay. So first I will show you the interconnections, how they are interconnected. That is very important. Actually, when I came last time, this is so, as I told you that I will, let's say, start from school level knowledge, wherever possible. So, some of these things I introduced when I came last time. Okay? Because you will understand it better. So, some of the things may be repetitive, but that will say enhance your learning process. So, here we will start, let's say, from 3D vector algebra, and all these, they are part of linear algebra, as I told you. So it is like this. Say, so first I will talk about two different problems. So I will introduce several items at a time. So let's say I am talking about the movement of an ant over a floor. Okay, at any given point of time, where exactly the ant is, if I want to know, I can draw a diagram like this, x-axis, y-axis, and I put the corresponding coordinates x, y over a point. I can immediately pinpoint relative to this some origin coordinate frame. I can tell where exactly the typical location of that. Now suppose I want to do this for a honeybee. So I am going from 2 degree of freedom to 3 degree of freedom system, because that can fly also. So as you can see now, those two coordinates, they are not adequate. Okay. So now let's say I am going for 3 coordinates, x, y, z, and now my point, let's say q, is function of x, y, z. So if I want to exactly pinpoint where exactly the honeybee is there, I need now 3 numbers. So 3 numbers written in a specific order, 3 ordinary numbers written in a specific order will give me the idea of the location, the position of any system or particle. Okay? And as you can see, that it's very easy to extend the dimensionality of my vector space going from 2D to 3D. So as you are going from 2D to 3D, I can go to 4D, 5D, 6D, exactly I will extend. But only problem is, as we live and perceive in a 3-dimensional world, it is difficult to visualize whatever is happening in higher dimensions. Okay, so we have to take the projections on 3D. Okay. But in principle, technically, in an abstract fashion, extending the dimensionality is not at all a problem in that. Okay. So in principle, suppose I can go for a, let's say, 30-dimensional space. I will call this, if I call, say, x1, y1, z1, x2, y2, z2, and so on up to xn, yn, zn. So this is basically 3n dimensional. Why it is required? Suppose if you have any n particle system, each particle will require 3 coordinates. So you will have a 3n dimensional space. That extension is also possible. Now, algebra. How will you do it? Algebra in a sense, suppose we are talking about the change in position, not only the position. So gradually I am entering into mechanics. Change in position means I have to know the velocity. If I want to be a little bit more perfect, I have to know the acceleration and all sorts of stuff. Velocity is not like position. You have to tell the direction in which it is changing and by which amount, let's say, per unit time it is changing. So you need both magnitude and the direction. Okay. So that means you are going from scalar to vectors. So suppose if you have a vector, say I have a vector, I am taking a 3-dimensional Euclidean space because that is most general and the simplest way of understanding it. So suppose this vector is OQ vector. If I call this vector as P vector, I write it as IPX plus JPY plus KPZ. Okay. But I, J, K, they are unit vectors along x, y and z directions, and Px, Py, Pz, they are called scalar components because they are not vectors. I, J, K are vectors. How much of I, how much of J and how much of K, if you take the linear combination, you see I am say terms, but they are having mathematical meaning. So what I am doing, linear combination of three base vectors. Remember, I am using another word is base vector. That means any vector, this is called closure theorem, any or closure axiom, that any vector, the vector space would be closed if any vector, arbitrary vector, can be written as the linear combination of those base vectors. So we know all Euclidean vectors, I can write it as a linear combination of I, J. But suppose if I take a vector from that 3n dimensional space, obviously I cannot write it as linear combination of simply I, J, K. We have to go for unit vectors also, that also will be 3n dimensional. Okay. Apart from this closure, there is another property. Another property is I dot I is 1, J dot J is 1, I dot J is 0, and so this means the vectors are normalized, these vectors, and also they are orthogonal. The meaning of this is these vectors I, J, K, they are orthonormal base vectors. So they are called base vectors, sometimes they are called basis vectors also. Okay, base vectors or basis vectors. But that is the basis of your expansion, linear combination. So you could extend this. Let's say if I call E1, E2 up to E3n, they are the base vectors in that 3n dimensional vector space. Then I can write any vector. Let's say if I have any vector P in that space, I can write this as P as E1 P1 plus E2 P2 plus E3n P3n. Okay, exactly the same way. So, and any three-dimensional vector can be written as a linear combination of these base vectors now, E1, E2, E3, E3. Okay, there are 3 and such numbers. Now we were talking about the vectors. Suppose if I write it like this, E1, E2, E3n, you can see if you take the product of these two matrices, I will get the same result. So here you have a row matrix, here you have a column matrix. Their product will give me this vector. So a vector is nothing but a product of two matrices. You can see. Actually you have learned that they are two different things, but they are actually interconvertible. And what I can see that any EI dot EI is 1 for all I, and any EI dot EJ is 0 for all I not equal to J. Okay. As we have done for IJK, here I can do it same for all E1, E2, E3. So if you take the same vector, there this is what we call scalar product. There is another product which is called vector product or cross product. So this is the dot product or the scalar product. So that why they are called scalar product and vector product? Because if you take the product, whatever product is produced, that would be a scalar. Product of two vectors will be a scalar. In case of vector product, if you take the product of two vectors, that will also be a vector. Okay. So that's why they are called that. So you can see they are normalized, all of them, and they are also orthogonal to each other. That means we are talking about, say, base vectors which are orthonormal. Okay. In general, how do you write? Ei dot Ej is written as Kronecker delta Ij. Now, what is Kronecker delta Ij? This is 1 when I equal to j, and this is 0 when I not equal to j. Okay, that is called Kronecker delta. Okay. So in this case, you can see how you can write say any in terms of this orthonormal base vectors, how you can express any arbitrary vector in that 3n dimensional space as the linear combination of those base vectors. Okay. Now we will see, suppose two such vectors are there in that space. I'm talking about 3n dimensional, we'll call this as the vector space. Okay. As I told you, I will assume that orthonormal basis vectors or base vector, the set is complete set. Complete set means whatever vector you have, you can always write as the linear combination of those base vectors. If it is not complete, you may get some vector which cannot be written as the linear combination of those base vectors. You need something else, but that is not there. That will not serve the purpose. Now all these terms, whatever I am using, they would be important when you go for the actual quantum theoretical calculations, compared to basis set, etc., etc. They are very important. Okay, so if you understand from the vectors, we will just translate it to the functions later, so that basis of functions will come into it, and not the base vectors. Okay. Now, in addition, we will require in quantum mechanics that it should be linear vector space. Linear, any linear operation means what? That if the operation is closed under addition and scalar multiplication, if it is closed under addition and scalar multiplication, so I am telling closed under what is the meaning? Suppose you have a resultant of two vectors. Resultant of two vectors, let's say R is P plus Q. If you can write P and Q as a linear combination of those base vectors, any such combination of two vectors or three vectors, whatever, can also be written as the linear combination of base vectors. That means your vector space is closed under addition. Okay. And scalar multiplication suppose if I have some Q is some, let's say 5 times P, this scalar number. So this vector, new vector, is a collinear vector, only the length of the vector is larger, but the direction is same. So that vector also can be written as the linear combinatorial, as long as this is finite. That means suppose if you have vector space like this, if you have something like 10 to the power 15 P, that also in principle you should be able to write in this case. Okay. Like in quantum mechanics, when you extend the basis, go for larger number of basis functions. Nowhere you will see that your computer will get exponential over, because it's linear. Okay, and the quantum mechanics is linear, that's why operators also follow the linearity. What do you mean by the operators following linearity? Suppose if I tell some operation, let's say taking a square root. So square root of a plus b is not equal to square root of a plus square root of b. That means this is a non-linear function. This is not a linear function. Or square, a plus b whole square is not a square plus b. There is something else, some other extra piece. Good. But suppose if we operate like ddx operator. If I call, say, ddx of fx plus gx, you know this is a prime x plus g prime x. And similarly, ddx of some constant into fx is some constant into a prime x. So what is the meaning? That whether you do the operation before adding or whether you do the operation before scalar multiplication, you get the same result. So that's why it's a linear operator. Differential operator is a linear. Okay. So linearity is very important. That's why I told you at the beginning that we are talking about linearity. Okay. Because the non-linear part is vast domain in physics. Non-linear dynamics like chaos, solitons, etc. If you want to understand, you have to go beyond the linear space. But luckily in quantum mechanics, it's a linear mechanics because the wave function will have to obey the superposition principle. Without linearity, superposition principle will happen. Okay. So, 3n-dimensional linear vector space, we will see the scalar products, let's say P dot Q. So, if I write this P dot Q, so you can see this is sum over I Pi into sum over J Ej Qj. Now you can see all possible terms will come. All possible E dot Ej terms will come. Only when I equal to j, those terms will survive. Other terms will vanish because your E dot Ej is Kronecker delta Ej, isn't it? Your E dot Ej is Kronecker delta Ej. So ultimately, what we get? P1 Q1 plus P2 Q2 up to P3n Q3n. So that is the standard scalar product definition you will learn from your school. But now you can see that the orthonormality of the base vectors will NCU, that will get the same result. Do you follow this one? Suppose you write it in longhand notation, P1 P1 plus E2 P2 plus E3 P3. This similar terms will be there, and they will give you, and there U1.1 is 1, E2.2 is 1, so they will get this. Okay? Now suppose, now we will go to the functions. And that is very important in quantum mechanics. But we will see, they follow exactly the same algebra as in vectors. So, functions, so what exactly do you mean by a function? Suppose if you have one-dimensional function y as a function of x, it means to get a curve in this xy plane, and getting a curve means for any value of this independent variable x, there exists a specific value for the dependent variable y. This much is the dependent variable, this much is the independent variable. Okay? And if you join them, you will get the curve. That is, or we will call that as the function. Now you can go to, this is function of only x, I can get function of x, y, z, and ultimately a function of 3n variables. Okay. So you get a 3n dimensional function space now, not the vector space, but a function space, 3n dimensional function space. Well, so when you get a function space, now the question would arise, can you talk about basis functions, like you talk about basis vectors there, so that any arbitrary function can be written as the linear combination of those basis functions? Can you consider the basis functions to be orthonormal as we consider orthonormal basis vectors? The answer is yes. That means now you can think about basis functions. Suppose if I call them basis functions as phi x, and for them the scalar product is defined because they are functions I star x, ij x integral. Okay. This is called the scalar product of two functions I and x. But here you have to take the complex conjugate. If they are real functions, there is no problem. But in general, in quantum mechanics, you may come across, particularly in a dynamical situation, you get, say, complex functions. So that is the definition of the scalar. But as you will see that every time writing integral, dx, etc., Dirac had given a prescription. So Dirac's bracket notation. So what happens that any function I x is written in the bracket form like this. Suppose if you have phi x, I will write it like this, and this is what we call it. And the complex conjugate, let's say phi j, is written like this. So this is your phi x is written in the kate form, and phi j star x is written in the what is called the bra form, is the kate form. And if you juxtapose them, what you get, phi j star x ix, the bracket is complete, so this gives you the bracket. But only thing you will see the additional c, so you have to take this operation, and that implies you are talking about this integer in the bracket form. So this is your I j star x, I x dx, and sometimes x is also not written because these are written in the vector and draw vector, because we are taking the language of vectors. So I write this as ij ix, simply like this. So this is your scalar product, okay, written in the bracket notation. We will follow the bracket notation again and again in different contexts, because now onwards this integral business I will try to avoid, because I don't want to write it again. Okay, so that is the scalar product. And you can see that if they are orthonormal base vectors, this is your Kronecker delta G. For the orthonormal base vectors, this scalar product for the same function will give you 1, and for different functions it will give you 0. So you can see that same language, whatever scalar product becoming your Kronecker delta Ij, here also you are taking Kronecker delta Ij. Okay. Only different, here you have a complex conjugate and integral. That is, because it's a function, unless you integrate, you have to get the number 1, 0, etc. That you will not get unless you do the integration. Okay. So now comes, so you have, let's say, a complete orthonormal basis set. Okay. Or precisely, if I want to say, a complete set of orthonormal basis functions. Okay. So if you have a complete set of orthonormal basis functions, any arbitrary function can be written as the linear combination of those basis functions. You see the language, we use the same language in case of vectors. So complete set, suppose if psi x is any arbitrary function. So in principle, I can write this psi x as sum over I, ci x. What does it mean? So if I have a complete basis set, I can always write any arbitrary function as a linear combination of the basis functions. I don't know how much mathematics you have learned. This is standard undergraduate say syllabus. It is there. Have you heard of Taylor series? Yes or no? No. Maclaurin series? No. Suppose if I ask you, you write the series expansion of e to the power x. What is the series expansion of e to the power x? Then e to the power x 1 plus x plus x squared by 2 factorial x cubed by 3 factorial. This is e to the power x. Okay. If I ask you sin x, you can write x minus x cubed by 3 factorial plus x to the power 5 factorial minus, that's the sin x. So you can see, I have learned these are all your Taylor series of Maclaurin series technically expansions of various functions. This arbitrary function e to the power x sin x, whatever arbitrary function you have, you can write. So suppose if you have a basis set x to the power n, x to the power 0, x, x squared, etc. I am writing as a linear combination, and this linear combination coefficients are like 1 by 2 factorial, 1 by 3 factorial. They are your CIs. Okay. So you have already learned how to do it in simple differential calculus. This is in schools. Perfect. So you have already learned what I have written written in that, you have learned that it can be done. Now these are the basis functions. Your basis function may be, these are called, let's say, polynomial functions or the algebraic functions. You can take trigonometric functions, you can take Slater functions, you can take Gaussian functions. Then you are entering in hardcore quantities. Okay? So you are writing the wave function as a linear combination of several Slater type functions, which are like your orbitals. Then each orbital is expanded in terms of Gaussians. You get your STO3G type stuff. One is Slater type is written again in terms of 3 Gaussians, and my wave function is written in terms of those newly constructed Slater type orbitals that you have been doing knowingly or unknowingly when you go for different types of basis sets here and there, 6311, G, etc. They have only variation in these basis functions, nothing else. Okay? So you have to learn this. So this is one part of the game. I am telling all components how you are developing for your quantum chemistry calculations. Okay? So if you have some, and you know your this phi I, phi j, this letter, this scalar product is Kronecker delta ij because I have started with orthonormal basis functions. Okay. Technically, it's not at all difficult. Suppose these, they are also, to start with, they are not orthonormal. But they are standard techniques, they are very easy. Normalization is nothing, is a 1 minute job. Orthogonalization is also a little bit harder. Gram-Schmidt normalization, orthogonalization technique is there. So what you can do, even if your original basis set is not orthonormal, because there are certain, say, technical advantage of using orthonormal basis function, because the cross terms will drop, isn't it? Otherwise, you have to have all possible cross terms that you have seen just now, isn't it? So they are like, if you have E1 dot E2, you put it 0. But then you want to do that also, you have to take. So sometimes we keep it as such, they are non-orthonormal. Sometimes we make them orthonormal through certain other technique and then use it. Okay, but you have to keep a track of that. Whether your starting part is orthonormal or non-orthonormal, then you have all cross terms that you have to be very, very careful. Okay, but when we mix the functions from here, there you have polarization, this is division, this is this, that. In general, they are not normal, and according to what happens, they will put what I call, when you write in the matrix form, some off-diagonal elements which will create trouble. Okay, so when you diagonalize the matrix, that is the reason why you have to diagonalize the matrix. If they are orthonormal, they will come always up in the diagonal. Off-diagonal terms will not. Otherwise, off-diagonal terms will be there. So, if they are heavily dominant, then they may create some trouble. Okay, but there are techniques depending on, of course, the size of the matrix and how much time, computer time you have. So all these are interrelated. But if you know the techniques, whatever is going at the background, then you won't have any trouble to identify where exactly I have to put some extra time and extra effort. Okay. Directions have no, this part, then go to matrix representation, there so maybe another 5 minutes. So I can write, you can see as phi 1, phi 2, phi 3n, and then C1, C2 up to C3n. So again you can see that a function, this function phi is written as a product of 2 matrices. Okay, so if I expand this, it is just, or I can write it in general, this is what we call, say, these are combination coefficients. So this is called coefficient matrix, and these are basis functions. So this is called basis function matrix. Okay, so construction of basis function matrix and this matrix you have seen. Okay. Now, what you could show that any arbitrary function phi x, if I know the basis, so you can see if you change the basis, this will change. For a given basis, different wave functions will have different c. This c is crucial, phi is not at all crucial. At the beginning, I choose my phi. Whether I am doing STFCC or C311G or C311G plus double star, phi is changed. But once I fix the phi, I go from water to ammonia, this C will change, that phi will remain same, as long as the base set is same. Okay, so I stop at this point and then maybe again, but I will have to maybe continue a little bit extra, because otherwise, say towards the end you will see that my plan is to tell all aspects of DFT, so that you can have a better understanding of reactivity for dynamics, say TDFT, basic principles of DFT, Kohn-Sum equations, and all sorts of stuff. Okay, you have to bring in the Hartree-Fock equation also in order to appreciate the Kohn-Sum equations. I don't think that you have any trouble, because these are all school of equations.
We have remembering all equations. All equations coming back from
Yes.
school level.
But what's the time by the way?
10, 11.
11.
So 10 minutes?
Okay, another 10 minutes maybe. Oh, you want to put there first?
No. But students, then only they will actively participate all in mathematics.
I am 68 years old. After your age, I am shouting, standing, you are sitting quiet, and you are getting bored.
But
you are too bad.
You are giving, sir, but we are gaining, we need some storage.
So this must transfer actually, you are getting late. Come on. So you are having more inertia.
No, you want to.
We have seen that any arbitrary function I can write in this form, that will have one basis function matrix and one coefficient matrix. Okay. Now we will bring in another concept in linear algebra, that is the operators. Okay. So suppose if you have an operator A which operates on fx, its job is to generate a new function. So that is basically the role of an operator. When it operates on a function, it generates matrices. One coefficient matrix, one basis function. What will be the pedagogy? Suppose if I talk about A psi x, it means A operating on phi. So these are numbers, coefficients are numbers, but these are functions. So all elements of this matrix are basically functions. You see, whatever you learned in general, the simplest way of writing a matrix is it's an array of certain numbers only. But this is a peculiar type of matrix where the elements are not numbers but they are functions. Okay, phi 1, phi 2, phi 3. Okay, if your basis function is a trigonometric basis, let's say. So there phi 1, phi 2, etc. are like sin x, sin 2x, sin 3x, sin 4x, and so on. If they are algebraic functions, they are like 1, x, x squared, x cubed, etc. So they are functions, not numbers. So when A operates this side, here A will operate on this matrix. Now we know when an operator operates on a function, what happens that we know. So we know that say ddx of sin x will give you a different function. That we know, isn't it? Or ddx of let's say x square will give me 2x, another different function. But when an operator operates on a matrix, what happens? That means it will go to the individual elements which are functions. C. Okay. That is my pi matrix. So individually, this is the property of the matrix pi 2. So separately, all the elements of this pi matrix will change. Because the operator will operate on all individual elements, which are functions to start with, and they will be now replaced by new functions which are generated through the operation of the operator key. So what is the fate, let's say, of this A phi 1? You remember this, I'll bring this back, but first let's analyze A phi 1. Then I will have some idea what would be A phi 2 also. A phi 1. Again, A phi 1, you see, it's a new function, new arbitrary function. So, as any arbitrary function can be written as the linear combination of my original basis function, A phi 1, which is a new function, also should be written down in terms of as a linear combination of my original basis function. So I am doing the same job, sum over I, phi I, A I 1. So meaning of this is, I am now writing A 1 1 phi 1 plus A 2 1 phi 2 plus A 3 1 phi 3. So A phi 1 is a new function, but now it is also written as a linear combination of my old basic functions. Similarly, if I call A phi 2, I can write this as A 2 1 phi 1
1, 2, and 1, 3. The other one should be 1, 2, 1, 3.
1 2 1 2 2 2 and so on, isn't it? Yes, it should be what? It should be sum over I, phi I, AI 2, isn't it? Because this one is the memory of that one, and A is coming as AI 5. Okay. That way you can remember. So this one is phi I AI 2. Then is phi 1 A1 2, phi 2 A2 2, then phi 3 A3 2, and so on. Isn't it? So this one, suppose I am writing this as phi A1. This I am writing it as phi A2. Okay, and so on. Okay. Why? Because your A1, if I call this A1 as A11, A21 up to A, say if I call only in AN1. Okay, in dimensions. Or I can put 3n also, A3n. Okay. See, my A1 vector is this, and phi vector is a row vector, row matrix into this matrix, so their product would be this one, isn't it? Similarly, this is A2 would be A12, A22 and so on. This is your A2 matrix, and similarly A3 matrix, A4 matrix, etc. Okay. If you don't understand, tell me. Right? So now you can see your A psi, remember, is A phi C. This is your A phi 1, A phi 2, A phi 3 and C. Okay. Your A phi 1 now I can write it as phi A1, phi A2, phi A3 and C. Okay. This I can write it as phi into A1, A2 up to A3n. Phi is common, so I can take it outside. Okay. I can put it like this. Suppose now I call this matrix as some matrix A. Can you tell what would be the dimensionality of this matrix A? Matrix should be 3n by something. So like this matrix, there are 3n rows and 1 column. It is 3n by 1 matrix. This is also 3n by 1 matrix. So whatever this A matrix, 3n by 3. Okay, so this is a square matrix. So A is a square matrix of dimensionality 3n by 3. How will it look like? A11, A21, A3n1, A12, A13n, A22, A23n, A3n1, A3n3. Okay, so this is the square matrix. Okay. So any arbitrary element of this matrix is what? Any arbitrary element of this matrix Aij is phi I, A operator, phi C. Okay. So this matrix A is called matrix representation of operator A in the basis set phi. This is very crucial. So this A matrix is matrix representation of operator A in the basis phi. Okay. So you can see now I am expanding or rewriting my operator business with the help of a basis set of functions in the form of a matrix. I should tell you, when you any quantum chemical calculation. You don't solve the differential equation, the Schrodinger equation. You have to convert the Hamiltonian operator to the corresponding matrix in the given basis set you have chosen. It is this matrix. Okay. You have to learn this matrix. And we will see what is the property of this matrix, etc. So that is the standard way, because they are, you see, typically they are matrix elements. So Aij is an element of this matrix. That is the common nomenclature in quantum mechanics. You see, Hamiltonian matrix element, this, that, etc. That means that basis set, if you construct the matrix with the basis set of the Hamiltonian operator, which row, which column I am telling, here Ij means ith row, jth column of this matrix. And diagonal elements are called expectation values. You can see, we will talk about expectation value when we go to quantum mechanics. That means diagonal elements means what? Integral ai star a operator ai, integral I star a operator I dx, any I, 1, 2, 3, etc. They are all diagonal elements. So all diagonal elements are expectation values. And off diagonal elements, in general, all of them we call them matrix element. Diagonal matrix element, off diagonal matrix element. But here you can see one important thing, that if the basis functions are chosen in such a way that they are eigenfunctions of the corresponding operator, and if it is orthonormal set, I am giving you this exercise, simple quiz. You can immediately see that their eigenfunctions means ultimately some eigenvalue will come out of the integral, and it would be what we call the overlap, say matrix element. It would be along the diagonal, that overlap element will give you 1, all off diagonal element will be 0. That means it would be automatically diagonal. Okay. So many times people choose that trick also to diagonalize. Along the diagonal, actually your eigenvalues are there. That means when you solve the Schrodinger equation, basically you have to get the energy eigenvalues. So energy eigenvalues would be just distributed along the diagonal of the matrix, Hamiltonian matrix. If you can properly diagonalize it, automatically you get your energy. That means you have solved the corresponding Schrodinger equation in the matrix. Okay. Now, two important factors. You can see your A phi is phi A. For the sake of completeness, I am telling some of the items which, if you are interested, because they are also part of your quantum mechanics and group theory that you have to know. And that is the way how you sometimes numerically diagonalize a matrix. Diagonalization of matrix is basically nothing but the solution of the Schrodinger equation via matrix. Okay. Now suppose for this phi, if I talk about this matrix, phi dagger, okay. So phi dagger means this is your adjoint or say Hermitian conjugate matrix. What does it mean? That you take original phi matrix, transpose it. Transpose means you make rows to columns and columns to rows, and take the complex conjugate of all the elements. Then you will get this phi dagger. And if it is orthonormal basis vector, your Heidegger phi would be a unique matrix, because it will have one along the diagonal and all off diagonal elements can see that if I put this type of matrix over here, then what I have, my Heidegger A phi is Heidegger phi A. That means unit matrix into A. And as I told you that if there your actually when I write this Heidegger A phi as A, basically it's a matrix definition of this. Okay, all elements are like this. Heidegger A phi, they are giving you the elements of A. So this is the specific version element, and this is the generalized matrix version of this. Heidegger A phi is A. Okay. So individual A element of A you will get from there, and Heidegger A phi you will just expand, you will get all these elements. There in the Heidegger A phi, that matrix will be your A matrix. Okay. Do you have any confusion? You can expand, as I told you, Heidegger you write simply complex conjugate transpose, then you write A and then you write phi, given method, and then you see apply the orthonormality condition, orthonormalization condition, and you will get back to the all the elements of the A matrix. Okay. So we talked about the matrix representation of an operator in a given basis set. Now if this operator is connected to some specific equation like Schrodinger equation, this is Hamiltonian. Hartree-Fock equation, that's your Fock operator. Kohn-Sum equation, that is your Kohn-Sum operator. Instead of solving those original equations, they are differential equation or integral differential equation. Basically, you convert them to the corresponding matrices in a given basis. Suppose if we have to solve the original differential equation or the integral differential equation, there is no question of basis. You have a differential equation, there are techniques for the solution of the differential equation, solve it. Like the way you solve the Hilbert problem, hydrogen atom problem. But for complicated systems like many electron atoms or molecules, complicated molecules, that is not the case. Then you have to take this view that you convert depending on which level of theory you are doing to solve, say, Hartree-Fock equation, the Fock operator, etc. To expand, you write that Fock operator in a matrix form, which you call Fock matrix. So we'll see later on, because the boys EOYS, we are giving the basis set expansion and other basis set expansion, and also Buchan that expanded. So this is sometimes called Buchan Hartree-Fock technique, where you just go to the matrix form, not the original Hartree-Fock equation. When you go to the matrix form, then you can solve the matrix equation. So that technique, how to solve the matrix equation, that may be tomorrow is a class. Tomorrow I will tell you how to solve a matrix equation. Okay, but before that, I have to tell you something about the equation, like Keep right. Simple operator DDX. Your basis set sin x, sin 2x, cos x, cos 2x. If you want to take orthonormal in, let's say, you take 1 by root pi, so there would be orthonormal functions 1 by root pi, 1 by root pi, 1 by root pi. So 4-dimensional basis, this is your operator, and let's say you do it in the limit 0 pi, because you have to integrate for all matrix elements. You take the integration limit as 0. So construct the matrix or the DDX operator in this trigonometric basis within these integration limits. Okay? It's very simple. So it will be a 4 by 4 matrix as your DDX matrix in this basis. So that will give you a clear-cut idea how you construct your basis set. May be very complicated basis set like 6 through 1, G, etc. And your Hamiltonian operator, Thomson operator, or Markov operator, and the corresponding limits would be set by the dimensionality of your problem. Okay? So this can be done analytically. You don't have to do analytically. This is very simple trigonometrical stuff. Okay? So you construct this matrix. Perfect? And another thing, you can see that these functions are not eigenfunctions of DDX operator, because they are going to get changed. But if I take d2 dx2 operator, they are eigenfunctions of d2 dx2 operator. So that also you can check d2 dx2, that is representation of d2 dx2 operator in this basis. As I told you, automatically it will be a diagonalized matrix. That Heidegger A phi equal to A that I had shown, it would be a diagonal matrix. That also you can see, d2 dx2. But for DDA, of diagonal elements will be present. Perfect? So if you are conversant with all these algebra, whenever you get the results from your actual quantum mechanical calculations, you know if you get a garbage, you will be able to immediately pinpoint that I am getting garbage. I should not accept this solution and send the paper right and send it to the journal, and the reference will point out that whatever you have selected is garbage. Okay? Now, I will just introduce something, and the remaining part tomorrow I will tell you. So first I will tell you the fundamentals of mechanics, that is ordinary classical mechanics. In the classical mechanics, there are different versions. So the popular ones we call Newton's version, where Newton has considered all mechanics in terms of forces. So if you apply force, how the state of the system is going to be changed. Then you have Lagrange equation in terms of action, and you have Hamilton's mechanics, Hamiltonian mechanics in terms of energy. And as in quantum mechanics we deal with energy only, we straightway start from Hamiltonian classical mechanics, not Newtonian classical mechanics. Okay, this will it's difficult to follow in quantum mechanics in terms of forces. Although there are techniques, but I am telling the general way how to develop. They are in terms of the Hamiltonians, and the Schrodinger equation basically is only on the Hamiltonian. Okay? So energy. So in the Newtonian mechanics, what happens is you have here you have a second order differential equation, here also second order, here you have two coupled first order equations, differential equations. So those equations you have to solve. That means if you know, say, any physical property in classical mechanics is a function of position and momentum. So position and momentum means if I call the position vector q for a 3n dimensional space, it would be q1, q2 up to q3n, and p is a momentum vector. So this is not that q is a vector. This means that I am talking about a multidimensional, say, matrix vector. Okay, that's why it is equivalent. It doesn't mean that q is a position. It's not equivalent. But it is given vector notation because it is 3 dimensional. It's not only one. So p, similarly p1, p2. But I am writing these are scalar components because the vectors I don't need. Scalar components are sufficient. Once I know the basis. So any function property in classical mechanics is a simple function of q and p. That means if you know the position of a particle, if you know the momentum of the particle, you know any arbitrary property in classical mechanics. So suppose at t equal to 0, I know q0 and p0. Okay, I know this at t equal to 0. Then I have this equation of motion. Equation of motion, like Newton's, Lagrange's or Hamilton's equation of motion. If I solve them, at a later time, I can tell what will be the position and what will be the momentum. That means I can get this qt and pt at any later time. And if I know this, I know the function over here, function at t equal to 0, I know the function at t equal to t. Okay, that means any property, how they are evolving in course of time for a given system. If it is Newtonian mechanics, that means I have to know what is the force acting on the system. If I know what is the force acting on the system, then I know that suppose its energy is this much or its any other property is this much. After a certain time, I can immediately calculate to the solution of that second order differential equation, the Newton's equation of motion. Then I can tell what will be the position, what will be the momentum, and for all particles, all the coordinates, all the momentum component, I can calculate and I can immediately put it in the functional form, and that will tell me what will be the corresponding value at that time. And that's why classical mechanics is called a causal mechanics. Causal in the sense there is a cause and effect relationship. If I know the force, I know the future completely. You can see, as I told you that at any given time t, I can exactly pinpoint what are the different functions of that particular body after a certain time, if I know the force acting on it. So the solution of this equation of motion. There is no ambiguity as such. I know it. Only problem is when you switch over to quantum mechanics, that luxury would be lost. I am not sure what should be the value. And we have to talk mostly on expectation values, not the number. So I don't tell this is the energy of the system, this is the pressure of the system, this is the viscosity of the system, this property of the system, this is the dipole moment of the system. After a certain time, if you do this, if you do that change, these are the properties. There will be change. That I can tell you as well. In quantum mechanics, I cannot tell. Suppose if I have this, how much can we expect the corresponding property of the system? So there is a basic difference in understanding classical mechanics and quantum mechanics. So for that reason, we have to somehow reformulate the whole mechanics. So maybe today was the time. So 15 minutes are there, no problem. So I can tell you something on postulates of quantum mechanics, how they are going to get changed. So when you can see that basically you require 6n variables to totally identify any given system, and not only that, if you know the force laws or whatever mechanics you are doing, whatever equation of motion you are doing, according to corresponding classical mechanical observable, and that will totally identify the future behavior of that particular system. In quantum mechanics, you are losing somewhere, you are gaining somewhere, losing in the sense that now it's not a simple function. Like I write it a functional form, I put the values of q and p and I get a number. You don't get a number so easily. There what you get, there you have to tell that in terms of the probability, not the number, the way classical mechanics were doing it. This could be the, no, that language is not acceptable. But at the same time, there is something called Heisenberg's uncertainty principle. So position and momentum you cannot tackle simultaneously immediately. And accordingly, what happens, either you talk in terms of the positions or you talk in terms of the momentum, and you get a coordinate representation quantum mechanics or a momentum representation quantum mechanics. Both are equally valid. You can, so depending on your choice, but mostly we talk about, say, for bound systems we cover the coordinate representation, and for scattering systems which are free, so there we go for momentum representation. So in this case, the coordinate representation, that means you talk about only one half, either q or p, so we will talk mostly about this q. What are the postulates? So in order to prove, you have to start with certain postulates. Okay, like Newton's equation of motion. You have to start with those what Newton showed, like gospel. Here also you have to start with certain gospel that if you believe in this, then only I can explain your experiment. So for any system, you'll get something called the wave function psi qt, where if I know the position of a particle, let's say I have some electrons q1, q2, etc., and at a given time t, I define this as the wave function of the system. So this is a function. But wave function is not the physical property I am talking about. It's a arbitrary function. And this function has one property, that if I calculate this quantity, this will give me the probability of getting the system at time t within q and q plus d. That volume. How much is the probability? But this one is integrated, so this will give me the total probability in the whole that coordinate, whatever configuration. So this is postulate 1. Postulate 2 is the operator postulate. For each dynamical observable A, which is a function of q and p, there exists some operator A, q operator and p operator. So if you know only the operator from qp and maybe t also, if you know, so it is very easy. So this one q is just multiplied by q, by x by x, y multiplied by y, time also multiplied by time. And these are the scalar components. So if they say along the x direction, Px, it should be like h cross by del x. So operator terms are fixed for your position, momentum and time. Now here you know what are the functional forms. You get the corresponding functional form and put the operator forms of x, p and t, that will give you the operator form of that particular dynamical oscillator. Like suppose if you have energy as Hamiltonian as kinetic energy, which is a function of momentum, plus the potential energy, which is a function of position, then H operator will be like for particularly one dimensional, say harmonic oscillator minus 1 by minus x cross square by 2 mu into ds2, because you have p square by 2 mu, okay, for harmonic oscillator plus half kx. So immediately you can write down the operator form of the Hamiltonian and construct the equation. So that I will tell you about the equation. So this is the operator question. Wave function you know, but where from you get the wave function? That is, for a dynamical system, you have time dependent Schrodinger equation, that is h psi as I h cross del psi del t, and for ordinary stationary conditions, suppose you are interested only in the structure, stability, etc., but not on the dynamic, then you get, it's only the spatial part of this, h psi is inside. So this is what we call time independent Schrodinger. So you solve this equation, get the wave function, you get the operator form, but then what? Operator form is with you, wave function is now with you through the solution of the Schrodinger equation. How will you get the corresponding property? Where in classical mechanics simply you put Q and P and got the numerical value. Here you get the expectation, and I told you what is expectation value. So expectation value of any property A is simply psi A. Psi, if it is not already normalized, this is the normalization part. So divide this by psi side, and that is your expectation value. So here you can see, this is simply your wave function, which you get as a solution of the Schrodinger equation. Operate this A operator, which you have already constructed, on side generating new function, multiply with psi star, integrate, and here you have the norm, psi star psi integral. You will get the expectation value of this. That means if you do some experiment, you are expecting that much value for that particular physical operator. Okay. So you can in principle check that if you know that these are the postulates, these are the steps, what in principle you are supposed to get. Rest are all details, numerical details and other computational details. Like if I ask you, which basis set will you choose? Like if you want to construct this, you have to get the basis sets. How will you choose this? How will you solve this equation? These are the details. But that also you have to know. What type of basis functions you should choose for a given problem, for a given property. For a given property to property also your basis functions will change. System to system will change. Suppose if you have a large system, dynamic system, you have to put too many this function. Then your common sense will tell you, but that is a kind of art, it is not science. Okay. So in this case, the part for science you have to learn. And here, what you are getting, another important thing is, like here, whether you are solving straight away that essay to say, or depending on the complexity of the problem, you are putting some water into it and getting a diluted version, that is your picture. Whatever is available, whatever say is your requirement, whatever say your numerical resources. So depending on your capabilities, depending on say your requirement, etc. Suppose if you are too over enthusiastic to calculate something very, very accurately, you have to go for some basis. But your computational power doesn't allow you to do this. You have to reduce think I stop at this point and solution of this equation. So first, this is an operator now. What would be the matrix form of this?